Alright, what we want to do is we want to use our knowledge of Hooke's law to understand a class of material called elastics, elastic materials. And these are the ones that we said they obey Hooke's law. When you do something to material, it wants to return to its original shape. Materials that do that obey Hooke's laws. Materials that don't, those would be like inelastic materials, and inelastic materials would be ones that try to change the shape, the change stays. So as an example of an elastic material would be like the marker. I squeeze on the marker, and when I remove the squeeze, the marker looks the same as before I squeezed. An example of an inelastic material, or one that doesn't obey Hooke's laws, is this yellow putty. Notice the shape of the putty. I apply a force, I squeezed it with my fingers. The shape of the material didn't go back to its original form. When I squeezed the marker and I removed the squeeze of the marker, the marker returned to its original shape. So what's happening, you can think about like at the atomic level, when you're applying forces, let's say you're trying to stretch the material or you're trying to compress the material, at the atomic level, the bonds between the atoms are being stretched and squeezed, and they act like little springs, right? So you're kind of like stretching. In this case, these guys are getting pushed together, and you're taking the little springs and squeezing them. In this case, you're stretching them, and then when the force is removed, the springs kind of go back to their original shapes. And that's like what happens in the marker. But elastic materials are what we're going to focus on because they obey Hooke's laws. Or how does our object change shapes when we apply forces? Well, what we can do is we can start with our Hooke's law. And we can think about when we apply forces to our object, how does that change the shape of our object? And we can think about the shape as being like the length of the material. So if we take a material and we start stretching it, we would change the length. So in that case, we'll call this delta L, the change in the length of the material. Now what we can do for K, when we're talking about a material, K we can rewrite as YA over L. And so what we can think about is if we're looking at, like, let's say a rod, or some type of rope or chain, or like some type of rope or material that's linear, like a rod, we can apply forces on the rod to stretch the rod. Now, as we apply forces onto the rod, what happens? Well, the K is a property of the material. And so how does that relate to this material? Well, Y is called the Young's modulus. And this is a number based on the stiffness of the material. It's like a number that we assign to materials based on their stiffness or pliability. So if Young's modulus is high, it's a very stiff material. The bigger Young's modulus is, the more stiffer. If the Young's modulus is small or low, then the material is pliant. It's more easily to change its shape. So that's what Y is. It's a number assigned to the material. This is a property of the material. It's a number assigned to the material. A is what we call the cross-sectional area. And that's what this area is here. It's this end unit. It's like the shape. It's kind of like the cross-section. If you look at the end of your cylinder, if it's a cylinder, it's pi r squared. If you're looking at some kind of rectangular shaped object, then what do you have? You have the cross-section of a square, which would be like height times width or something like that. And so that would be the cross-section of that. So it's the shape that's related to kind of like the shape of the material. And then length is related to the actual, how long is your material? It's much easier to get the longer the material, the easier it is to get a small stretch out of it. If you had like a 10 meter long rod, you could stretch that 10 meter long rod a small amount. But if you had a very tiny rod, it's much harder to get a stretch out of that because you'd have to start thinning the material much faster to get some small amount of stretch. So if we're looking at the forces needed to cause changes in length, and this is some kind of related to the shape and property of the material, which is what our K is, then we can substitute in this new value for K, and what we see is that the force needed depends on this Young's modulus, the cross-sectional area, and the length, and the change in the length is related for how much force you get a certain change in length depending on the shape and properties of the material you're trying to change. So we can use this new equation to calculate how forces are going to change our objects. And our two things that we can look at is if we stretch the material, when we stretch it, that's called the tension force, a tensile strength. Tensile forces are when we stretch. Compressive forces are when we squish it. And the Young's modulus will normally, it can have a different force, a different value depending on whether we're stretching or compressing. Another way we can think about this is how do these materials respond? We can think about plotting our forces against our changes in length. And what normally happens is there's a region where the material responds elastically. It'll follow some Hooke's law relationship, and as you apply the force and you remove the force, it'll go back elastically. Now, there's a small region where it will still go back to its original shape, but it won't do it anymore using Hooke's law. It will follow some other law. Then as you continue to apply the forces, so that up until here, you were still going back to your elastic shape. You're still elastic in some fashion. But past this point to this point, here when you apply the changes, the material is changing shape now. You're no longer in the elastic limit. You're past that, and your object, the changes you make are permanent to your object. And then here, at the very end, this is when the material fails. And when the material fails, you've broken it. Like the material fracture, break, something happens to the material and it fails. And for us, like stretching and compressing the object, this is called the tensile strength. Is how much force the object can take before failing. And the tensile strength is related to the maximum force that the object can take divided by that cross-sectional area. And what happens is you can look these numbers up because like engineers and people have gone in and tested materials till they know the failure, and then they measure the force that was required for that failure, and then they make tables of these things. So the tensile strength is how much force the object can take before it fails. So when we're looking at materials follow this where we have force. How much force you apply to the material changes the length, and that depends on the material and its geometry. And our materials that we're looking at are going to follow this elastic relationship up into some point. Past that point, they will have some kind of permanent change, and then you hit the failure limit where you have the maximum force, and that's the tensile strength at that point. Now, another way to look at this relationship is the following, over A. And then we have Y, and we'll just move the L under the delta L. And F over A, this is called the stress. It's how much force you apply to your material. Y is still the Young's modulus, and over here, delta L over L is defined as the strain. So what we see is we have stress equals Y times the strain. So how much force you apply gives you some kind of change in the material dependent on the stiffness of the material. So if Young's modulus is high, you get small changes for big stresses. If Young's modulus is small, you get large changes for the same amount of stress. So the idea is you apply some stress, which is like our force, and you get some change, And how much change you get in your material depends on Y, the Young's modulus, which is that property of the material, whether it's stiff or pliant. Remember though, this is still under Hooke's law, so it'll still go back. It's just how much change in the length do you get. And just as a simple example, the Young's modulus for steel is 20 times 10 to the 10. So steel this is considered one of the stiffer materials. Something like spider web is 0.3 times 10 to the 10. So spider web, you would, for the same, if you had the same size, like a little cable of spider web and a little steel cable, you would see that you could apply the same stress to both of them, but the spider web would change much. The change in the strain on the spider web would be much greater than on the steel cable for the same amount of force. So this is just another way of thinking about our Young's modulus equation here. So we've taken a look at how forces can change, like the ideas of forces and changing the shapes of objects, like the lengths of objects when we apply forces.